So this is going to be the first of 3 videos using Eigenanalysis. So this first one will just use the stiffness matrix, so the system stiffness matrix K that we've already calculated. So the Python script is going to be very straightforward. But what I will do is build a few extra component groups, really just showing how you can normalize the displacement output that you get from the eigenvector, so that we can ensure we plot that on a sensible scale. And obviously you could take the techniques used here and maybe apply them back, for example, to plot the bending moment diagram on a suitable scale. So I'll leave that for you to explore. So the first thing we're going to do is obviously get our new Python component. So we'll just zoom in here. And actually the only input that I need is the K matrix. So just noting here that this means that this is not dependent on the loading that we've applied. It will be dependent on the boundary conditions because obviously we adjust the K matrix for that. And then in terms of the output that I want from here, so I am going to get a list of eigenvalues, and then the other output that I want is a list of eigenvectors. So these will be the columns in the eigenvector matrix. And when we have a look at the Python script, which we'll do in a second, you'll see there are just some additional, so there's one additional line here. This brings in basically a Python library that helps us assemble trees within Grasshopper, and then these few additional lines here just allow us to output those trees. So it's another sort of way of just ensuring some consistency in how the data is being handled within Grasshopper and within Python. But the actual line to calculate the eigen or carry out the eigenanalysis is just here, and you can see that produces eigenvalues and eigenvectors. I do then sort through the eigenvalues to make sure these are in order, and then just we order the values and the vectors on the basis of that sort. And the other thing we do is we just bring across the real part of each of those. So occasionally we'll be given some other parts, and this just kind of sorts all of that out. Okay, so I'm going to do Control A here to select everything, Control C then to select it all, and then we'll go back into our Grasshopper. So it'll just take a second or so for the script to open up. So there we have it, and I will just paste that in, so Control V to paste it all in. Save that, and obviously at the moment it's not doing anything because we haven't brought the K matrix in yet. So we will just go and fetch our K matrix, although before we do that I will just set it up with a relay here, just to help me visualize as everything's going around. And over here we have this K matrix. I think I've just been experimenting, so I'm going to enable this again on that relay. So we're just running the relay across to there, and you can see that's now happy enough. We will just set this for the type hints. I'm going to say no type hint, but you can see it transferred in okay in any case. For the outputs then, so the type hints that we want here, these are both going to be floats, and so there we have it. So we can obviously just put in a panel for the particular setup that I have, which is still the portal frame. You can see the list of eigenvalues there, so they quite quickly increase, but you can see the lowest ones will help us identify the modes that the structure is most likely to deform in. So we'll come back to that obviously when we get to look at the eigenvalues. Okay, so the eigenvectors should have been output as a tree, and we can see that if we just hover over there. There's a clear tree structure here. So what I want to do is just select a tree branch, and that's going to allow me to select the particular eigenvector that I want to plot. So we'll run it here. I need to simplify this. So obviously I only want to choose one branch. It will always output a tree with this sort of data structure. So basically the 0 that's the first number in the path, that is always going to refer to the trunk, and then the second number 0, 1, 2, 3, 4 and so on, that refers to the branch. So we're always going to get a tree output in that format, but it's the tree branch that we're interested in. I'm then just going to introduce a slider. So this will be to allow me to select my eigenvectors, or as I'm going to call them here, eigenmodes. Generally the first sort of 10 or so are the most interesting, so I'm just going to enable my slider to go between them. So we've got the eigenmodes coming in here, and then the eigenvector obviously is outputted as displacements at each of the nodes. So we're going to have our partition list component. So I'll just bring that across. I left the bifocals around here somewhere. There we go. So I'll just turn that on so you can see. And what we want to do here, so obviously we have 3 degrees of freedom at each of the nodes. So we're going to partition that list every 3 items. And then I want to simplify here. So then the list items, what I'm aiming to do is create a vector, which is obviously how I'm then going to display everything. So I want to run my list in here. I am just going to turn off the wrapping, and then I can zoom in here. So I have got basically the displacements in the x direction, displacements in the y direction, and then rotation around the z-axis. And what I want is just to define my vector. So I'll just take the x and the y. We can't visualize that rotation really. And you can see here everything is fine, but what I'm going to do is also flatten the output here. So we don't need that branch structure anymore. And then the next few stages, so obviously here I've got the length, for example. So I'm going to use bounds here. So that allows me to just output, and it will give me from 0 to whatever the value is. I'm then going to construct my domain. So just construct domain like so. So that'll give me a start and an end. Because the length is always positive, I don't actually necessarily need the next component that I've included on the canvas image. So I can always just take the end, and that will allow me to scale things. And basically I want the 1 over, so 1 divided by, we'll bring that up. So that is giving me a scaling factor that I can use to normalize this so that the amplitude is effectively always 1 in terms of what we're doing. So I will be including that in a multiplication component. We want the vector in that component. This next one will then do the normalizing. And then what I am going to have, so I've got a further normalization or scaling to deal with in a second, and then we'll actually have a magnification component coming in here. So some of the way that I'm putting all of this on the canvas is just related to how I want to display everything, and also that I'm going to include this in a component, because obviously we will replicate this for our other eigenanalysis. So I'm just going to say that I want to vary this between plus and minus 0.1. And basically that means that it's going to be 10% of the overall largest dimension that shows up when we plot the eigenvector. So I'll just do that there, and I will call this slider magnification in there like so. Just check our spelling there. Okay, so and then I will connect this up ready. So obviously the next part that we're going to do is we're going to look at this scaling compared to the overall dimensions. So what I want to do is I'm going to bring in my original nodes as points. So bringing them in, I'll just select that and indicate these are going to be the original nodes. So that's basically the undeformed nodes, and these are back here. So I'll just take them over to that component that I've just added in. Just find it there. And to try and sort of keep things a little bit neater, I'm just going to right click here, go to the wire display and select hidden. Otherwise I'll end up with trailing wires all over the place. And then the other information that I want to bring in is I want to bring in the list of element nodes. So I'm going to bring that in as a data set, and we'll just label that as element nodes. And these were from over here. So this was our list of start and end nodes for each element. So I'll bring that over like so. And again, we don't really want that wire trailing around. So I'll just go in here, right click, and then I can set the wire display to hidden. So we'll come back to use that in just a second. So because I want to set this up as a component grouping in a little bit, I'm actually going to copy these original nodes over to here. So we will be using them again in just a second. So I've got that information. Down here now, there's another component that we haven't really discussed before. So this is the bounds 2D component. And what that will do is it allows me basically, we can see, so for this portal frame in the U direction, or we might know it as the Y direction, the dimensions go from 0 to 4000, and then in the V, or the, well, X and Y, rather, the plane we're working in, so in the V or the Y direction, the dimensions here in this case go from 0 to 3000. The next thing we can do is we want to deconstruct that. So there are actually a couple of options. You'll see deconstruct domain 2 and deconstruct domain 2 down here as well. So I believe the one that I want is this one, and you can see that gives me all of these components like so. So what we can now do, we'll just do the negative here and negative here as well. So essentially what we're doing is we're just finding out the range in the X and the Y directions, so that's why I'm swapping around the inputs as I do it here. And then a rare occasion when we will use the maximum, because we obviously just want whatever the maximum range. So in this case, it's the 4,000 that we want to end up with. So that brings us through to here, and that we will just join in there. So we can do a little bit of grouping now. So I'm going to call everything in here up to there. I will call this normalizing the eigenvector here. And then these few components down here, we'll just group them as well. And this I'm just going to refer to as scaling the magnification. Obviously what we're doing is we're scaling based on the overall dimensions. Okay, so we're almost there in terms of what we're doing. The next thing that I want to do, so I've got this information on the element nodes, so I want to explode the tree here. So that basically just gives me the start and end node for each one of them. What I can then do, or what this is going to allow me to do, is obviously draw the elements as well. But in terms of just displacing or moving the nodes to display, what I want to do is just run the node in there, and then this here is now the vector that we're going to move each node by. So we can just have a quick look there, for example, and we can see what we're aiming for here in terms of that first eigen vector or eigen mode here. So we can then just use the list item, as always, turning this wrap off, and we'll have another list item there. So what we're doing here is just taking the original nodes, running them in as our list, and then obviously we want the start nodes as our item, the end nodes as our item, and then what I'll do is just use lines to join all of these. So this set of lines are my original elements, and again, because I want to create a component here, I'm just going to bring these outside, or where I'll be about to bring them outside. So we'll call this set here. I'll just change that to original elements like so. Now that we've moved, obviously what we can do, we can have another set of points here. So these are now our displaced points. And what we're going to do is again create just lines from them. So we'll have list item, remembering to set that to false for the wrapping. Another list item here. And again, we'll set that to false. So now it's the displaced points that are the list items we're interested in. And we can again choose our start and our end nodes. And we will just feed these into a line component again. So like so. And again, I want to bring that line component outside the component package that I'll create in a second. So we'll just group that, and I will label that as my eigen vector elements. So we'll just space these out a little bit here. So then the final sort of things I want to make sure that I can just preview back in Rhino. So I'm going to bring this through here. So these are my original nodes, and then the other one that I'm likely to want to plot are these ones. So these were my eigenvector nodes, so we'll just group and call them eigenvector nodes, like so. And then I'm just going to group all of these, including that multiplication one there. So I'll group these, just shift them around a little bit. I'm going to just align them all. Okay, so this we'll just refer to as is plotting the eigenvector. So what we could do now is, for example, if I have the original elements, the eigenvector elements, you can see over in Rhino, and this was the 0 eigenmode. So this is basically giving an indication that this is the easiest way. So this is the way of deforming the portal frame, in this case, that has the lowest stiffness value. If we run to 1, you can see another quite straightforward or relatively flexible way. And then as I run through these, some sort of increasingly less likely deformation modes, and you can see these are associated with increasing stiffness values. So once we're up to the value associated with, say, 10 or 11, we are several orders of magnitude higher in terms of the stiffness mode, and you can see that the potential displaced shape is sort of getting increasingly unlikely. But it is a useful check. So if we go back and just alter our boundary conditions, for example. So we've gone back and I'm just editing the boundary conditions. So I'm deliberately setting these up so that they actually produce a scenario where we don't have sufficient restraints or sufficient boundary conditions. And what you can see is if I go through here, we have some extremely low, so very close to 0 eigenvalues. And what that indicates is that we are likely to have a mechanism. So either in this case we have rigid body motion, or if we had other combinations of things, it would demonstrate if we have a mechanism. And you can see that actually we have a negative value as well. So this is really just showing that it won't sustain any load without rigid movement. So I'll just go back and fix these. So putting them back in, and you can see now we have much more as we would expect. What we can also do is just show, for example, if I increase the stiffness of the beam that we're using, so I'm going to increase the depth to 100, what we would expect and what we see is obviously all of these values increase. So it increases the stiffness, but we'll find if we look at the likely displacement modes, so the eigenmodes, and just adjust these back, for example, to 0, we have the same order essentially. So the very final step here then, so I want to keep obviously my original nodes and my element nodes. This is information we're feeding in. We're feeding in the eigenmode and the magnification, and obviously over here we've also got our eigenvectors are going to be fed in. So this is everything we want to put in our component, because we're also getting the original nodes, eigennodes, original elements and eigenelements out. Okay, so we were just here when we're about to put all of these components in a cluster. One thing, just to make sure that the output appears in the order we want from the cluster, I'm just going to move this point down the way. So what this ensures is that our original nodes are the highest, our eigenvector nodes are the next down, then our original elements you can see are the next down, and then the eigenvector elements are the next down. So just going in, and it's all of these ones that I want. So I'm just going to put them into a cluster like so, and you can see everything is correct coming in and out here. So I'm just going to go through and alter the names here. So here we have original nodes, and obviously actually coming out we have the original nodes as well. Then we have the element node information coming in, and then obviously we have the eigenvector or eigenvectors that we were putting in. Then we've got the information on the eigenmode we want. So eigenmode there, and then the final input is the magnification. So in also coming out then we have the eigenvector nodes. Just correct the spelling of original up here. And then we have the original elements. And finally the eigenvector elements. Sorting out the spelling there. Okay, so I'm just going to bring all of this a little bit closer in. So just do a quick bit of rearrangement here. So original nodes, element nodes, obviously the eigenvectors, that's coming from the Eigenanalysis, which is the Python component, and then eigenmode and magnification. And then from over here, we can drag all of our outputs that we're interested in. And then I'm just going to group those, and I'm going to call that group plotting the eigenvector. And then final thing, because I know I sometimes forget, but we really don't want to forget, so just saving the file up here. Okay, so in the next couple of videos we'll look at using the geometric stiffness matrix for carrying out the eigenanalysis, and then finally using the mass matrix for carrying out an eigenanalysis. So see you back for them.